Why all the students are not there? Only 35 students are here.
Sir, I have dropped message. They are coming.
Okay. So first I will explain you that because this Wednesday is holiday, है ना,
Okay, sir.
according to
Yes,
the
sir.
state
Yes,
government.
sir.
So because we have to complete the experimental work, thermodynamics and the design.
Yeah, yeah.
So I have,
Exactly, sir.
है ना, so I have already given you the two experiments, practical experiment, and
Yes, sir.
I have given you as a assignment in the thermodynamics as well as the design. So first I will discuss that part. So in the thermodynamics, I have given you the two experiments, experiment number 7 and experiment number 8. In experiment number 7, this is basically the Gibbs-Deham equation. This you have studied the activity coefficient or not?
Sir, activity coefficient, sir, in the thermodynamics.
Yes, yes.
Sir, currently, sir, we were on chapter 11. I guess no, sir. Sir, it's the upcoming part now.
In next few lectures, madam will teach you about the activity coefficients. Basically, activity coefficients are used to modify the Raoult's law. So Raoult's law, you have studied the Raoult's law. All of you have studied the Raoult's
Yes,
law.
sir.
And
Yes,
the
sir.
problems will come in the test. And in coming test, the which madam will take the surprise test. In that test, madam will give you the problem related to the Raoult's law and the bubble point problem and the dew point problem. So you have to practice that problem from the book.
Okay,
All
sir.
problem, and that madam have you already given you the some
Assignment.
example assignments.
Yes, sir.
Just
Shared.
practice that problem. So what is the Raoult's law? Raoult's
Sir,
law tells you about the
relative lowering of vapor pressure is.
it tells you that the how the equilibrium will work in the solutions. So basically, this is the partial pressure in the vapor. Suppose you have a mixture of the solution, mixture of two or more components in the liquid phase as well as in the gaseous phase. There is a closed container which contains the liquid of the solution, which is a solution of the component A and B, and the same components in the gas phase. So this is the liquid phase, and this is the gas phase. So Raoult's law tells you that the partial pressure of the liquid phase should be equal to the partial pressure of the gaseous phase. So basically, whenever you study the mass transport, the driving, I have in the transport phenomena. Now I am going to start the mass transport. In the transport phenomena, driving force of the momentum transfer is the pressure difference. If you have the pressure difference between 2 points, the material, the momentum will start to flow, and the material will transfer from one point to the other point. The driving force for the heat transfer, the main driving force for the heat transfer is the temperature difference. Okay. Now, what is the driving force in the mass transfer? In the mass transfer, if you have a same phase, suppose you have a gas mixture, there are two containers which contains the gases. Okay, here you have the composition A plus B. In the other container also you have the A plus B. Both are in the gas phase, same phase. Then the driving force for mass transfer is the concentration difference. Okay, the driving force of the mass transfer is the concentration difference. But suppose you have the different phase, like in this case, you have the liquid and gas. Now here suppose the concentration of in the liquid you have the 40% or the 0.4 mole of the component A and 0.6 mole of component B. Now what is the concentration of the liquid in gas phase? So here driving force is not the concentration difference. The driving force, the mass transfer, is not the concentration difference if you have the multi-phase system in the mass transfer. Here the driving force is called the chemical potential. Chemical potential is represented by mu. It is the pure thermodynamic property. It cannot be measured. It can only be calculated. Chemical potential. It is a hypothetical property, because in the heat transfer you studied the driving force, if you want to transfer some material or something, and any property you want to transfer from one point to the other point, there should be a driving force. Then only material will be transferred. then there should be a resistance also. Resistance also. So resistance and driving force, and the product of both will control the amount of material transfer. And so resistance is inverse of diffusivity. Okay, so there is a diffusivity and there is a driving force. So when you have the two multi-phase system, so concentration cannot be a driving force. There are other factors which will affect, and which will decide the how much material will transfer from one point to other point. Okay, so these factors, the in thermodynamics, to make the system easy to understand or to make the system easy to calculate, so what people have do, they include all the factors which may affect the mass transfer and which may be driving force for mass transfer, and give the name chemical potential. So chemical potential is nothing which is not a quantity, actual quantity which can be calculated. It is basically represent any property which work as a driving force. Suppose material is transferring due to the heat, due to the temperature difference. So chemical potential may be equal to temperature difference. Suppose material is transferred due to the pressure difference, then chemical potential will be pressure difference. Okay, so any force or any property which act as a driving force for mass transfer is chemical potential. Thermodynamically, chemical potential is represented by the partial Gibbs free energy. So you will study this thing. So dg, this is the Gibbs free energy, by dxi, where xi is the ith component. Suppose you have the ith is I represent the number of components in the mixture, 1 2 3 4 5 up to the n. Okay, at constant temperature, at constant pressure, at constant xj's. So basically chemical potential represent how much Gibbs free energy will change when you change the concentration of component I, when other properties like temperature, pressure, and the mole fraction of the other components are constant. Okay, that is the chemical potential. So in this case, in the case when you have the liquid mix, liquid and gas in the system, in this case driving force is the mu, is basically the, you will also study this in the thermodynamics, mu will equal to the partial pressure, pi, and that is the partial pressure. So partial pressure is represented in the gas system. Partial pressure is represented by Pyi. This is for the gas. And for liquid, partial pressure is represented by Xi Pi set. Pi set is the vapor pressure. So this is for the liquids. So mass transfer will occur when these two quantities are not equal. These two quantities are not equal. So when you subtract the one quantity to the other, that will represent the total amount of material transferred from the liquid phase to gas phase or gas phase to liquid phase. Okay, so this is the driving force for mass transfer. If system is in equilibrium, equilibrium means the thing is transferred from the liquid to gas or gas to liquid, then Pi equal to Xi Pi set. This is the Raoult's law. And this is the Raoult's law, which represents that when the system is in equilibrium, then material mass transfer cannot occur. And the equilibrium is the amount of liquid vaporized should be equal to amount of gas condensed. And the concentration should also be same. And that should not should also be not constant, not changing. So the concentration should also not changing. That means Pi set equal to Pyi equal to Xi Pi set. P is the P is the total pressure. Yi is the mole fraction of component I in gas. Xi is the mole fraction of component I in liquid. PI set is the vapor pressure. Okay, so this quantity represents the equilibrium inside the liquid gas system. Okay, now this equation is true, or this equation is true when the solution is the ideal solution. So there is one more thing which you have to understand. This equation is true when the solution is the ideal solution, or in other terms you can say partial pressure of liquid is equal to XIPI set when the solution is ideal solution. So when you have the ideal solution, then only this quantity represent the partial pressure. Otherwise, this is not the partial pressure. And what is the definition of ideal solution? Ideal solution means the partial property should equal to the total property that I have already explained you in the previous classes. Hai na? Ideal solution means suppose you have the two components, component A and component B. So here in the component A, this is the molecules of component A. This is the molecules of component B. So if the both type of molecules are similar, है ना? And there are when you have the mixture of the whenever you have the compounds, then there are intermolecular forces. Okay, so there are some interaction between the molecules, okay, which define the physical properties. Basically all physical properties are due to the intermolecular forces. Okay, so there are some intermolecular forces in component A, there are some intermolecular forces in the component B. Suppose these forces are not equal, or the interaction between the two molecules of component A is different than the interaction between the molecules of A and B, है ना? So when you mix it, you will have the mixture, some dots. Now if the interaction, if the interaction between in the mixture of the molecules in the mixture, that is different than the individual components, then the solution is not ideal solution. Ideal solution means the the interaction between these molecules are same as they have the interaction between the molecules when they are the individual components, and when they are not mixed. Okay, so if the molecules have the different interaction, then the properties will start to change. Suppose this has the density 1000, this has the density 500, and B has the density 500 kg per meter cube, A has the density 1000 kg per meter cube. Okay, now when you mix these two compounds, if the interaction between the molecules are similar, then the density should be 750. The average of two quantities, kg per meter cube. The density should be 750 kg per meter cube. Okay, but if the interaction will change, if the interaction will increase or decrease, then the density will also fluctuate. Okay, suppose the density, you will find the density is now 900. 1 minute. Huh. So suppose density, you will find, if you find the density is not the average of the quantities, now density is 900, that means the individual density of the components are changed inside the solution, है ना? So if density is 750, that means the molecules of the component A has the density 1000 and molecules of component B has the density 500 inside the solution also. That's why average density is the 750. Now if density is 900, that means either this density, the density of component A is increased, or density of component B is increased inside the mixture. Another, due to the change of interaction between the molecules. So this is called the partial properties. This density is called the partial properties. Partial properties means in the solution, if the density of solution is 900, so how much part of the 900 comes from component A and how much part of 900, if the rho is 900, so how much rho comes from rho A and how much rho comes from rho B. Okay, and because this rho A and rho B is not the actual density of component A and B, so it is called the partial property. And the partial property means it is the density of component A and component B inside the solution. That is not equal to the density of the pure component. So rho A is not equal to rho A dash and rho B is not equal to rho B dash. So you understand the ideal solution? Ideal solutions are the solution where the partial properties are equal to the true properties, and or the interaction between the molecules are remain as it is when you make the solution. It is not happened whenever you have the solution. Suppose salt, and at the normal temperature, salt is present in the solid form. It is a crystalline structure. Why it is a crystalline structure? Because the interaction between the NaCl molecules are very high when you have the solid, when you have the simple salt. When you mix the salt in the water, then that interaction will become weaker. And because the hydrogen bonding occurs with the water molecules and the NaCl molecules. That's why the salt start to dissolve in the water. Okay, so the properties is changed. So that is not an ideal solution. And the ideal solution means the interaction should remain the same. So salt water solution is not an ideal solution. So here we understand that the Raoult's law is only true for the ideal solution, and most of the solutions are not ideal. Although there are several solutions which may consider as the ideal solution, but several solutions are not the several solutions are not the ideal solution. And when you don't have the ideal solution, then you cannot use the Raoult's law. Okay, so that's why we modified the Raoult's law. And because we have to solve the problems, we have to understand what is the driving force in the mass transfer when you have the liquid gas mixture. But that Raoult's law cannot be applied, so we modify the Raoult's law. And for non-ideal solution, the partial pressure of the liquid can be calculated by a new equation, gamma I pi set xi. Okay, so here one more component is coming, gamma I. So gamma I is called the activity. So basically activity is a thermodynamic quantity again. It only represents how much deviation has occurred with the ideal solution. So when you deviated from the ideal solution, so how much deviation occur? Okay, so activity, if the activity coefficient is 1, that means you have the ideal solution. Any value apart from 1, you have the non-ideal solution. So you have the modified Raoult's law, which tells you that Pyi should be equal to gamma I pi set xi. Okay, here gamma I is the activity coefficient. Okay, activity coefficient is the function of concentrations as well as temperature. Okay, now the problem is how to calculate the activity coefficient. Okay, so activity coefficient can be calculated by the several equations. So one equation is based on the Gibbs-Graham equation. Okay, so in this experiment number 7, I have given you the two equations. So this is the equations which can be used to calculate the activity coefficient of the acetone water mixture. Okay, one represent the acetone, two represent the water. Okay, A12, A21 are the constant values are given here, 2.0400, 1.5461. Okay, what you have to do, you have to make a program, just type this equation. Here you have to substitute the value of A12 and A21, 2.0400, 1.5461. just substitute the value of x1 and x2 these and calculate the activity coefficient gamma 1 and gamma 2. Okay, so values are given here, just you have to calculate the value of the gamma 1 and gamma 2. Any problem in this experiment? You can do the programming. This is the very simple program, just you have to write these equations. And just substitute the value of a12 a21 these and substitute the value of the mole fraction x1 and x2 and x2 are given here. You can use the for loop also, and if you want you can use the for loop or you can make the simple program also. Okay, any question?
सर बेसिकली यही करना है कि फॉर्मूले में जो जो वैल्यूज है उसके अकॉर्डिंग पुट करके बस आउटपुट निकालना है, राइट?
बस आउटपुट निकालना है ना. Basically
ऑलराइट
this is
सर.
not related much related to the programming, this is basically related to the understanding, है ना. So once you have the value of gamma 1 and gamma 2, then only you can calculate the, you can use the Raoult's law for the non-ideal solution, है ना. So this is the one equation, one model which can be used in experiment number 8. You have the another model that is called the Wilson model. This is also very important equation. So this is slightly more difficult model, है ना.
यस
है ना,
सर.
है ना. Here again you have to just substitute the value. So here you have the four temperature, different temperature. At each temperature the values of constant are different. Okay, so here you have the this, in this table you have the values of constant, here you have the mole fraction. Okay, so here again you have to just substitute the values here and the determine the value of gamma 1 and gamma 2. So you have to just modify this equation. You take the ln at other side, you will get the exponential of this quantity. Enough. You can do this. Okay, and then you can just substitute the values and calculate the gamma values of the gamma 1 and gamma 2. This is also very easy program. Okay? Any question?
नो सर.
ठीक है. अच्छा, one thing I want to tell you that you have to submit the program within time because the 25 marks for the experimental and this is the part where you can score. And what I will do,
ओके सर.
15 marks I will 15 marks are based on your submission and 10 marks I will take very easy quiz, one quiz, and based on that quiz I will give you the 10 marks. Okay, so 15 plus 10, 25 marks is on the experimental part, or I will give you the 20 marks for the submission and 5 marks for the quiz. Okay, so you
ओके
can
सर.
score 20 marks if you submit the all experiments within time. ठीक है.
Sir, the time is, sir, what's the time like? It's on 15th November or before 22? Oh,
Uh, no, it's before. It is on 17th November.
okay,
You
sir.
make it
All the
on,
experiments, right, sir? All
yeah,
the experiments.
all the experiments, है ना.
Okay, sir.
So I will award you the 20 marks if you submit all experiment within time.
Yes, sir.
Okay.
So thank you, sir, because sir, we have already just, sir, the average of the class has been low due to this CTS and ST of the subject. Thank you so
Okay.
much, sir.
Okay, है ना. So I will give you the 20 marks for that purpose only. ठीक है. So now comes to the next part, that is the design experiments. Engineering design. Engineering design, I have given you the same problem which I have given you in the exam. Okay, just the values are different. You have to solve that problem. Okay, pressure vessel, because we have not done anything new in this part. So you have to just design the
Okay, sir.
exchanger, storage vessels based on the data given in the here. Okay, that is the same problem which you have solved in the class as well as in the exam, class test 2. Okay.
Yes, sir.
Okay.
चलो ठीक है. Now we will start the class. So in the last class, we have started the mass transfer. So first I quickly revised the different components which we have studied in the last class. So basically, suppose in the mass transfer deals with the transportation of the different components from in the mixture from one point to the other point. Mass transport. So here, suppose first we will study the different definition used in this mass transfer in this part of the transport phenomena. So here generally we deals with the multi-component system. Okay, so for multi-component mass transfer, suppose you have the mixture of the component 1, 2, 3 up to n. This is the multi-component where you have the n number of components. So first thing you have to define the mass concentration. So mass concentration is defined as rho I equal to mi divided by Vt, where mi is the mass of component I. And Vt is the total volume. Rho I is called the mass concentration, but it is not the density. है ना? It is the rho I is the mass concentration, but not density. That you have to understand. है ना? Because the density is the mass per total volume when you have the pure component. है ना? It is in the mixture, so it is not the density. Okay. When you add the all mass concentration, you will get the density of the mixture. Till rho n. When you add all, you will get summation of I equal to 1 to n rho I, that is the density of the mixture. Okay, now we define the second quantity, that is the mass fraction. So mass fraction is defined as Wi, that is equal to rho I divided by rho, or you can say rho I divided by rho 1 plus rho 2 plus rho 3 up to rho n. So in the chemical calculations, heat and mass balance, you have studied these all quantities. Okay, or you can say rho I divided by summation of rho I from I equal to 1 to n. This is the mass fraction. Second is the molar, now the next quantity, that is the molar concentration. So molar concentration of component I is represented by Ci. Here this notation is also important, because in some problem you will find the mass concentration, in some problem you will find the molar concentration. So you have to stick with the notation. Rho represent the mass concentration and C represents the molar concentration. Okay, generally in books you will find the same notations. Okay, Ci equal to Mi divided by Vt, where Mi is the number of the moles of component I and Vt is the total volume. You can write, now you can represent the C. C is called the total concentration. Molar concentration means molar concentration of component I. Now similar to density, you can define the C. So C equal to C1 plus C2 plus C3 up to Cn, where C, or you can write C equal to summation of Mi divided by Vt, I equal to 1 to n, or you can write M1 plus M2 plus M3 up to Mn divided by Vt. Vt is the total volume. So this is called the total concentration of the solution. You can also write C equal to summation of Ci's, I equal to 1 to n. Okay. Now, after define the total concentration, you can define the mole fraction. Of component I. Okay, it is represented by Xi. Here again, you have to stick with the notation. W represent the mass fraction and X represent the mole fraction. In mole fraction also, X represent the mole fraction in the liquid and Y represent the mole fraction in the gas. Okay, so this is the normal universal notation used in the different fields. Okay, so Xi equal to Ci divided by C, or you can say Ci divided by C1 plus C2 plus C3 up to Cn, or Ci divided by summation of Ci, I equal to 1 to n. So this is the mole fraction. You already used mole fraction in the mass energy balance a lot. Okay. Now you can convert the mole fraction in the mass fraction. So that is the Ci equal to rho I divided by MWI, where MWI is the molecular weight of component I. Now, after defining the concentration, we have to define the velocities. Okay, velocities are also important in the mass transfer, because when the components are moving from one point to other point, then the concentration difference occurs due to the differential velocities of the molecule. Suppose you have the molecule of carbon and molecule of helium. So helium molecule is very small than the molecule of carbon. So of course, when the molecules move from one point to the other point, when they diffuses from, and it is called the diffusion. When the molecule diffuse from one the point to the other point, then helium molecules will diffuse much quicker than the carbon molecule. So the velocities of the molecules are very important. So we will define the average velocities. Now next quantities are the average velocities. So in a diffusing mixture, the components are moving at different velocities. Due to the mass transfer of components from the higher concentration to the lower concentration, or high chemical potential to the lower chemical potential. Basically, whenever you discuss the mass transfer, the driving force should be the chemical potential, because there might be a single phase, there might be the multi-phase. Okay, so I have already told you that the chemical potential is a driving force in the mass transfer. Due to the mass transfer of components from high chemical potential to low chemical potential. Okay, so which is, so for that we have to define the velocities. Okay, so the first is the mass average velocity, the first quantity which will define the mass average velocity. So mass average velocity is the actual velocity which you can measure. Okay, by equipments. And when we say the velocity of the system is this, velocity of the water is 2 liters per hour, or the 2 meters per second. Okay, so here we are defining the mass velocity. And when you measure the velocity, that is the mass velocity. So mass average velocity can be defined as V, that is equal to rho1 V1. Rho1 is the mass concentration of component 1. Rho1 V1 plus rho2 V2 plus rho3 V3 up to rho n Vn divided by rho1 plus rho2 plus rho3 up to rho n. Up to rho n, or you can write V equal to summation of I equal to 1 to n rho I Vi divided by rho I. Okay, so here rho represent the mass concentration, V represent the velocity of individual component. So first component velocity is V1, second component velocity is V2, third component velocity is V3. So you can calculate the average velocity of the solution. Okay, so whenever you measure the velocity, that is the mass average velocity. Okay, Now, second type of velocity is the molar average velocity. So when this is the hypothetical velocity, and this velocity cannot be measured, okay, because here the average is based on the moles. So whenever you measure the velocity, you cannot measure the molar average velocity. You can only measure the mass average velocity. This velocity can be calculated from the molar average velocity, okay, from the mass average velocity. So molar average velocity is V star, that is represented by the C1 V1 plus C2 V2 plus C3 V3 up to Cn Vn divided by C1 plus C2 plus C3 up to Cn. Okay, so this is the V star. It is the summation of Ci Vi divided by C, or you can write whole summation I equal to 1 to n Ci Vi divided by Ci, because C equal to summation of Ci's. Okay, this is the molar average velocity. This is the hypothetical velocity, okay, or supercritical velocity. Okay, now you can define the diffusion velocity. So whenever, why the average velocities are important? Because when you know the average velocity of the system, then only if you subtract the any individual component velocity from the average velocity, you will get the actual velocity of the that component. Okay, so now we will define the diffusion velocity. So how the diffusion velocity is important? Suppose you have a system. Here you have the two components. One component is represented by the dots or is circles, and the other component is represented by the cross. So here you have the circles and cross which represent the different components. Now suppose the velocity of dot is 1 meter per second. The velocity of the cross is 2 meter per second. So now how the concentration of, because the cross is moving more with the more velocity than the dots and than the circles, so the concentration at the end you will get the more cross than the circle. Okay, but how you will measure the actual difference, that how much concentration difference will occur, how can you measure? For that you have to first calculate the average velocity of the system. Suppose the concentrations are equal 0.5 0.5 weight percent, then the average velocity is 1.5, and then you can calculate the diffusion velocity. So diffusion velocity is the diffusion velocity of crosses that is equal to 2 minus 1.5. 1.5 is the average velocity, that is V. This is the V2, this is V1. So the diffusion velocity is defined as V2 minus V, or for the second component. For first component it is V1 minus V, and for the first component. Okay, so that tells you how much fast, how much relatively fast or slow a individual component is moving in respect to the whole components. Okay, that's why diffusion is important, because when the all components are moving from one point to the other point, then the mass transfer is depending upon the how individual molecules moving with respect to the other molecules. Okay, so that is important point. Okay, so now we will define the relative velocities or the diffusion velocities. So that can be represented by the Vi minus V, or this is the relative velocity in terms of mass. In terms of moles, you can write Vi minus Vi star, V star, Vi minus V star. That is the relative velocity in terms of moles. Okay, so you have defined the velocities also. Now we will start with the actual quantity, that is the fluxes. So like the in the momentum transfer we have the shear stress. In heat transfer we have the heat flux. In the mass transfer we have the mass fluxes. Okay, so now the new quantity which we will define is the fluxes of the mass fluxes, mass or molar fluxes. So first we will define the fluxes. So what is the flux? So fluxes are defined as the mass or molar flow of any species per unit area per unit time. Okay. So fluxes are defined as the mass or molar flow of any species per unit area per unit time. So basically it is the kg per meter square second or kilomole per meter square second. Okay, so it represents, suppose this is the cross sectional area, or this is the pipeline where material is flowing from one point to the other point. So first you have to know the speed of molecule, the amount of material in the terms of mass, how much material is transferred from one point to the other point, then divide by the time, you will get the mass flow rate, and then divide by the cross sectional area of the system, and then you will get the per unit area. So you have the kg per meter square second, and the flow rate divided by per unit area, you will get the flux. Okay, now we will define the different types of flux. Okay, so for that we will make the table. So types of fluxes, there are different types of fluxes. Here you have the mass flux and molar flux. These are the two types of fluxes based on the mass or based on the moles. And then you have the based on the conditions, or based on the, basically conditions are same, but based on the observer, position of observer, where observer is situated. Okay, so based on the position of observer, you have the different types of fluxes. Okay, first is the absolute flux and second is the relative flux, and relative fluxes are also the two types. So first condition with respect to the stationary observer. It is called the absolute flux or total flux. Or it is also called the total flux. Okay. So if you are calculating the how it is explained, I am giving you one example. Suppose there is a river. Inside the river, you have a water as well as the fish. Okay, you have the fish also and water also. Now you are situating outside the river and you are measuring the velocity of the fish, and you are counting the how much fish are moving from a given point. And you are situating at point A and you are counting the flux of the fish. How much fish, the amount of the concentration of fishes which are moving from one point to the other point. Okay. So here you are measuring the absolute flux because you are not you are not taking account the velocity of the water. So basically fish is also moving, water is also moving. So basically you are measuring the total amount of flux. When the observer is outside the system, then it will calculate the absolute flux. Okay. So if you have the mass flux, then it is represented by the n, small n, I. It is a vector quantity. It can be calculated as rho I, the mass concentration, multiplied by Vi. Vi is the velocity of that component. Okay. So rho I is the kg per meter cube. Vi is the meter per second. When you multiply it, you will get kg per meter cube multiplied by meter per second. You will get kg per meter square second. So the unit is the flux unit. Okay. So you will get the mass flux. Molar flux, absolute, you can calculate the same thing in the molar. When you have the molar, it is represented by the capital Ni. Capital Ni, you have to remember the notations because notations are important in the mass transfer. So capital Ni represents the molar flux, absolute flux. It is represented by Ci multiplied by Vi. So the unit of Ci is kilomole per meter cube. Unit of Vi is meter per second. So the total unit will become kilomole per meter square second. So this is the molar flux. Now, similarly, you can calculate the relative flux. So relative flux are also the two types of relative flux. When you are moving with the average velocity of the mass average velocity of the system, and when you are moving with the molar average velocity. So how to define the relative fluxes? Basically, suppose you are taking a boat and now you are moving with the velocity of the water, and now you are calculating the concentration of the fish. So in this case, basically the difference is due to the actual movement of the fish, not the movement of the water. So you have removed the effect of the movement of the water. And then now you are actually calculating what is the diffusivities of the fish, or what is the actual velocity of the fish inside the water when you are moving with the water. Okay. So that is called the diffusive flux or relative flux. Okay. And the diffusive flux is two types. One is when you are when you are moving with the mass average velocity, and second is when you are moving with the molar average velocity. Okay. So Now, with respect to the observer moving the mass average velocity, to the observer moving with mass average velocity, that is called the relative or diffusive flux. And with respect to observer moving with the molar average velocity, that is also relative and diffusive flux, but with respect to the molar average velocity. It is also called the relative and diffusive flux, but it is represented by the different notations. Okay, so here it is represented by the Ji, small j, when you have the observer moving with the mass average velocity and you are calculating the mass flux. It can be calculated as rho I multiplied by relative velocity vi minus v, where v is the mass average velocity. Okay, similarly you can calculate the molar average velocity when the observer is moving with the mass average velocity. It is represented by the capital Ji, it is the small ji. Here both are the vector quantities. Okay, so capital Ji, it can be calculated as Ci concentration multiplied by Vi minus V. Vi, V are the mass average velocities. Vi is the actual velocity of component I, and yeah, V is the mass average velocity. Now, in case of the observer moving with the molar average velocity, it is represented by the Ji star. So Ji star equal to rho I multiplied by Vi minus V star. V star is the molar average velocity. Similarly, capital Ji star, it is represented by the Ci multiplied by Vi minus V star, where V star is the molar average velocity. Okay, so basically you have the absolute velocities, absolute fluxes, as well as the relative fluxes or diffusive fluxes. Okay, absolute fluxes means when you are when the observer or you are the outside the system, and you want to calculate what is the actual velocity, what is the actual diffusion, and with respect to the positions. Okay, and relative when you are calculating the actual diffusion of a given component with respect to the whole moving system, and with respect to the whole solution or the mixture of the components. Okay, so diffusive fluxes are important when you are calculating the mass transfer from a moving fluid. Okay, and absolute fluxes are important when you are calculating the mass transfer in a stationary fluid. Okay, so when we will solve the problem, you will see sometimes we use the absolute flux, sometimes we use the diffusive flux, है ना, based on the requirement. Okay, based on your requirement, what you want to calculate, है ना, based on that you can use the absolute flux as well as the diffusive flux. There are correlation also between the absolute flux and the relative flux that we will study in the next class. Okay, so you have to remember the three types of flux, the two type of fluxes, absolute and relative flux. The relative flux is also two types, that the relative flux based on the mass average velocity and relative flux based on the molar average velocity. Then you have the mass flux and the molar flux. Okay, so that these definitions you have to remember in the mass transfer. Okay, this is enough for today's class. We will continue this topic in the next class. Any question? Okay, so we will meet on Thursday afternoon. Okay. So we will cover this topic, then we will start the presentations.